Covalent bond cleavage. The breaking of chemical bonds is called cleavage or fission. There are two types of fission. Homolytic fission, also called radical cleavage, occurs in a non-polar bond involving two atoms of similar electronegativity. So it must be a non-polar bond. A single bond between those two non-polar bond atoms breaks symmetrically into two equal parts, leaving each atom with unpaired electron, resulting free radicals. We know that in a single bond, there are two electrons, and the single bond break, one electron goes to one atom, another electron goes to another atom, leaving one unpaired electron, resulting free radicals. The second type of cleavage is heterolytic fission or ionic cleavage. It occurs in a polar bond involving unequal sharing of electron pair between two atoms of different electronegativity. In contrast to this one similar electronegativities, heterolytic, different electronegativities, and the bond must be polar, still between two atoms. A single bond breaks unsymmetrically. Why unsymmetrically? Because both the bonding electrons are transferred to the more electronegative atom. So in one single bond, there are two electrons. Both electrons in the single bond transferred to more electronegative atom. So in heterolytic fission, you must identify which atom is more electronegative, and two electrons will transfer to that atom. Homologic fission. This non-polar bond, two electron, non-polar bond, two atoms, same electronegativity. One electron goes to one atom, another electron goes to another atom. The bond breaks symmetrically, resulting free radicals in the presence of UV light or sunlight. Free radical is species which has unpaired electron. If you see an atom which has one unpaired electron, written like this, it is free radicals. Free radicals are reaction intermediates. They are very reactive, and many may only exist for split second. It won't exist like this for a long time. Only exists for a split second. The movement of single electron is shown by a curved half arrow. This is curved half arrow. Half-headed arrow shows, or it means, one electron only. If you draw fully headed arrow, it means two electrons are transferred. If half-headed arrow means one electron is transferred. The reaction are often catalyzed by sunlight, UV light, or you might see heat as well. There must be in presence of sunlight, UV light, or heat. Then this homolytic fission will occur. If there is no sunlight, no UV light, there won't be homolytic fission. They won't be producing free radicals. Heterolytic fission. The breaking of the bond can happen in two ways depending on electronegativities of the carbon atom and the atom Y. Atom Y is the atom which attached to the carbon atom. So, the positive charge of carbon is called carbocation, while the negative charge of carbon is called carbanion. So, if you look at this bond, it is covalent bond. Two atoms with different electronegativity occur in polar bond involving unequal sharing electron between two atoms of different electronegativity, heterolytic fission. Both electrons transferred to more electronegative atom. So, carbon and bromine is more electronegative, so the bond which consists of 2 electrons. These 2 electrons, both 2 electrons will be transferred to more electronegative atom. Bromine is more negative than carbon. That's why it's labeled delta plus, delta minus, more negative, more positive. So both electrons goes to bromine. So when it goes to bromine, this carbon will be called carbocation, positive charge, leaving carbon charge positive. So this is carbocation. If the reaction, you have carbon here and 2 hydrogen, carbon, single bond carbon, carbon, single bond carbon, 1 hydrogen, another 1 hydrogen. So carbon and hydrogen, hydrogen is less electronegative, carbon is more electronegative than hydrogen. So, and this one, the nucleophile attacks the hydrogen, hydrogen more electropositive means less electronegative, carbon more electronegative. Both electrons transferred to the carbon because carbon is more electronegative, leaving 2 electrons at this carbon, and this carbon is negatively charged. It is called carbanion. Carbocations are electrophile or Lewis acid. Carbanions are nucleophile or Lewis base. Relative stabilities of radicals. So we have three. We have free radicals, and then we have carbocation, we have carbanion. Free radical, this is methyl, primary free radical, secondary, tertiary. So primary carbon, because 1 carbon attached to it, secondary carbon, 2 carbon attached to this carbon, tertiary carbon, 3 carbon. So we want to look at the stabilities of these 4 molecules or these 4 radicals. Methyl is less stable than primary carbon radical. Primary radical is less stable than secondary. Secondary is less stable than tertiary, means tertiary is the most stable form of radicals compared to all of this. Most stable radical form from left to right. Increasing alkyl substitution, increasing radical stability, means if you have primary carbon, only 1 carbon attached, less stable than 2 carbon attached, less stable than 3 carbon attached to this carbon. And the carbon that you look at must be carbon-free radicals, because we're looking at relative stabilities of radicals. Why? Because radical carbon is electron deficient. If you look here, carbon need 8 electrons to achieve octet. Now here, the carbon has 3 bonds, 6 electrons in total, and 1 unpaired electron. So this carbon has only 7 electrons. Carbon must achieve octet. So when it has only 7 electrons, it is electron deficient. Means the electron is not enough. Electron pool, the electron is not enough. They are stabilized by substituents such as alkyl group. They are stabilized by the alkyl group. So this hydrogen, if you compare hydrogen and carbon, this R is carbon attached to carbon. So carbon and hydrogen, carbon is more electronegative than hydrogen. So when carbon is more electronegative than hydrogen, it's like this carbon is most likely light electron than hydrogen. So when it is more electronegative, it's like it's not giving, but it holds electron. This holds electron as well, but this carbon has more electron. Hydrogen only has 1 electron. Carbon will have like another 3 single bond here. So it's like holding more electron. So it's like this carbon has attached to the carbon that has more electron. It is electron deficient, so it likes more electron to attach to it. This hydrogen has only one electron only, and that one electron is shared. But this carbon, one electron is shared, and it's holding another 3 single bond. So the carbon in here is stabilized, this free radical stabilized by this carbon because it holds more electron. It means it likes the electron that attached to this carbon. That's why they are stabilized by substituent. Now you have 2 carbon attached to it, so more electron in this carbon, more electron in this carbon. If you compare this one, hydrogen, carbon. So carbon has more electron than this hydrogen. Hydrogen only 1 electron, and the 1 electron is shared. But this carbon, 1 electron shared, and it has more electron attached to other atom, more electron attached to other atom, and this one more electron attached to other atom. So the number of electron that this carbon holds stabilizes the free radical. Because this carbon is electron deficient. It is electron releasing group. Alkyl group is electron releasing group, electron donating group because it is holding electron. That's why electron releasing group or electron donating group. In this case, because it's holding electron, this carbon needs electron because it is the electron deficient. If it's attached to the carbon that is holding electron, makes this free radical is more stable. So number of alkyl group increase, the stability of radical also increase. Next, we look at the stabilities of carbocation. Same like in free radical, carbocation, the carbon is positively charged, means it is electron deficient, less electron. So the reason is the same. The reason is the same. It would like to hold electron. This carbon would like to hold more electron because it is electron deficient. So this carbon would love to attach with an atom that is holding more electron. Like this R. This R is holding more electron. This H only 1 electron. This R holding more electron. Plus this electron, this carbon is electron releasing group. So it's releasing electron. Okay. So that's why if it is attached, if this carbocation is attached to more C or more alkyl group, it is more stable. The reason is just the same as the free radical, because free radical, 1 unpaired electron means 7 electron in total, but for this one only 3 bonds, so 6 electron in total, more electron deficient than the free radical. The reason is the same. Why tertiary carbocation is more stable? It is the same reason as the free radical reason. Number of alkyl group increase, stability of carbocation also increase. Next, relative stabilities and carbanion. Carbanion, the carbon is electron rich. It has 8 electrons. 2, 4, 6, 8. Electron rich. It already has enough number of electrons. So when electron rich, it's like more electron rich, the stabilities is in contrast to free radicals and it is in contrast to carbocation. So the less number of alkyl group, 3 alkyl group, 2 alkyl group, 1 alkyl group. The less number of alkyl group attached to carbanion make it more stable. In carbocation and in free radicals carbon, if it has more number of alkyl group, it is more stable. But in carbanion, if it has less number of alkyl group, it is more stable because this carbon is electron rich. Increasing alkyl substitution, decreasing carbanion stability. Why? When the carbon ion is electron rich, this is the area where it is holding high electron density. The high electron density, more electron here, and then more electron will be given from these three alkyl group. This alkyl group is electron releasing group. Okay, it is holding electrons already. This is holding electron, and this alkyl group would love to donate electron, but this carbon is already electron rich, already have a high number of electron. But the presence of alkyl group wants to donate electrons to this carbon. So it makes this condition less stable because it's holding high electron already, and the carbon is electron releasing. This carbon, this alkyl group carbon, want to release electron to this carbon, but this carbon doesn't want that to happen. That's why they are destabilized, less stable. This one less stable than this one, less stable than this one, less stable than metal. So metal is the most stable because it has high electron density already, so it doesn't need other alkyl group to release electron to it. That's the reason. High electron density destabilized by substituents such as alkyl group. Because alkyl group is electron releasing group or electron donating group. So number of alkyl group increase, the stability of carbon ion decrease. This carbon ion doesn't want more electron because it has enough, or it is electron rich already.